They're kind of the invisible beating hearts of global commerce. I'm talking about these massive marine diesel engines, the ones that power the ships moving pretty much everything you own. But keeping these giants from literally melting down, well, that is a monumental task. So today, let's dive into the fascinating engineering behind how it all works.
So yeah, that's the big question, isn't it? When your engine is several stories high, you can't just bolt a radiator to the side and call it a day. The amount of heat we're talking about is just immense, and the solution has to be every bit as massive and robust.
And to solve a problem that big, engineers didn't just come up with one solution. Nope, they developed a whole series of increasingly clever and complex answers over time. It's really a fantastic story of engineering evolution, and we can break it down into 3 major designs. And this really shows you the whole journey. You can see how we went from a super simple open-loop system to a much more protected closed-loop setup, and finally to the big one, the highly integrated central cooling system that you'll find on most modern ships today. The open-loop system is about as direct as it gets. Seriously, think of it like taking a garden hose and just spraying down a hot engine block. You suck in raw ocean water, pump it through all the different coolers for the engine's jacket, the pistons, the oil, and then you just dump the now hot water right back overboard. Simple, right? But there's a huge hidden danger. And here is the massive catch. Seawater is just nasty stuff to put inside a machine. It is incredibly corrosive. It's full of salt, sand, little bits of marine life, you name it. Pumping that directly through your multi-million-dollar engine is, well, it's playing with fire. And that huge problem is what led to the next big idea. So enter the closed-loop system, and honestly, it's a brilliant solution. It works a lot like your car's radiator. You have a clean, controlled loop of fresh water that circulates inside the engine itself. Then, you use a completely separate loop of seawater just to cool down that fresh water in a heat exchanger. The absolute game changer here is that the corrosive, dirty seawater never, ever touches the important engine components.
Okay, so now that we have this nice, protected internal loop, a new question comes up. What do you actually fill it with? You could go with pure distilled water, that's the top shelf stuff, but it's expensive. Plus, you have to watch it carefully so it doesn't become acidic. So, the industry standard is just fresh water. It's cheap, it's available, but the catch is that its impurities mean you have to get serious about adding chemicals to stop gunk from building up.
And this brings us to the king of them all, the central cooling system. The real genius here is just consolidation. Instead of having seawater pipes running all over the place, you restrict all that raw seawater to one single, super robust circuit with a couple of huge central coolers. This central hub does all the work, cooling down all the different freshwater loops for the engine and everything else. The result? You've massively reduced the risk of corrosion for the entire ship.
All right, so you've got your fancy, advanced cooling system, you're feeling pretty good. But even with the best design in the world, there's a common enemy that's always lurking inside the pipes. This is the stuff that really keeps engineers up at night: contamination.
And this cross-section of a clogged pipe, it tells the whole story. You can see the 3 main bad guys at work. First, you've got sand and sludge just building up, blocking the flow and creating dangerous hotspots. Then you see the oil sludge, which coats the inside of the pipe like a blanket, completely killing its ability to transfer heat. And finally, the worst stuff: hard mineral scales. This is basically like cholesterol for the engine's arteries, choking off flow and trapping heat. A total disaster.
So just to recap, you're fighting 3 distinct villains here. You've got sand and sludge, which literally choke the system. You have oil sludge, which insulates it and stops it from cooling. And then you have scales, which kind of do both. Any one of these is a direct path to a catastrophic engine failure.
So how in the world do you fight this enemy that's already inside the system? Well, this is where the engineers have to put on their chemist hats. They've got a whole toolkit of chemical treatments they can deploy to keep that cooling water doing its job.
But of course, it's not that simple. It's a classic engineering dilemma, a balancing act of trade-offs. For example, on one hand, you've got something like sodium nitrite. It's cheap, it's easy to find, and it works really well. The big downside, it's toxic. On the other hand, you have emulsion oils. They're totally non-toxic, super easy to handle, but if your system is already a little bit dirty or has some rust, they're completely useless.
And this chart, wow, it really shows you just how complex that decision gets. An engineer has to weigh the cost, how well it works, how toxic it is, but they also have to know exactly what the pipes in their system are made of.
because if you pick the wrong chemical, you can actually cause way more damage than you prevent. It is a very precise calculation.
Let's just take chromates as a perfect example from this chart. The first thing you see is rapid, effective, and you could even check the concentration just by looking at the color. Sounds like a dream come true, right? Well, then you look at the box right next to it, highly toxic and harmful to hands. And that, right there, that one trade-off, perfectly captures the kind of high-stakes decisions these marine engineers are making every single day.
Okay, so let's bring all these different pieces together. When you look at everything, what is the modern strategy for keeping these absolutely colossal engines cool and running reliably?
It really all boils down to these three core ideas. First, you need the best architecture possible, like a central cooling system to minimize your risk right from the start. Second, you have to play proactive defense, which means rigorous, constant maintenance to stop sand, sludge, and scale before they can even start. And third, you need chemical precision, carefully, surgically, selecting the exact right treatment for your system's specific needs.
And that combination, smart architecture, constant defense, and precise chemistry, is the state of the art right now. But it does leave you with a final thought. As engines get even more powerful, more efficient, and run even hotter to meet new environmental rules, well, the demands on these cooling systems are just going to grow. So what comes next? What new materials or designs or intelligent systems will we need to meet that challenge? That's the question facing a whole new generation of marine engineers.